It's a pleasure to introduce Jun Ha. He had undergraduate studies in Korea, and then he had a doctorate from Michigan in 2014. So you see he's likely the youngest plenary among the plenary speaker at this meeting, but he gained immediately a very high reputation for the quality of his results, and he worked he's still working in a very interdisciplinary method among geometry, algebra, and combinatorics, as you see from the title of his talk. So I leave him the starting of the talk. You see the title. Thanks.
Thank you. Thank you for the invitation, and thanks for coming. I'm really happy to be here at Rio, wonderful place, and also to participate in this meaningful event. So, as you may have noticed, I am neither Brazilian nor Italian. But there is something Brazilian and Italian about the mathematics that I'm going to talk about. So in a sense, the results that I'm going to present was created in an effort to combine two old but important ideas. And of course, one idea came from a Brazilian mathematician, and the other idea came from an Italian mathematician. So that's my Brazilian-Italian connection. So the title is Hodge-Lefschetz theorem, Hodge-Riemann relations. I'm going to tell you what are those. The point is that there's not only one Hodge-Lefschetz theorem and not one Hodge-Riemann relations, but there are many such statements. This is an observed fact. We don't know why it happens, but for some reason, the same type of structure shows up in very many different type of mathematical objects. So let me try to tell you what Hodge-Lefschetz theorem should look like in general. Certainly, we haven't found out them all. So let's say you have an object X. X is a mathematical object. And I want to be sufficiently vague so that I cannot be possibly wrong. So let's just say X has sufficiently rich structure, whatever that means. My impression is that the condition we are looking after has something to do with the notion of convexity. But again, I don't want to be very precise. So we have our X. What do you want to prove about X? So here are some known, but before going to that, let me show you some list of examples that qualified as having sufficiently rich structure. So one example may be a compact Kähler manifold. So that's some special kind of complex manifold which is characterized by the condition that it admits a very special type of non-degenerate closed two-differential form, which is positive in some sense. And maybe the standard example of such an example would be the quotient of the affine space C to the D by a lattice lambda. So you may recognize the familiar picture of an elliptic curve as a quotient of the affine line. That has sufficiently rich structure. Or your X may be a convex polytope, say of dimension D. So it's the convex hull of finite set of points in the real vector space all to the D. You can think of any one of your familiar polytopes, maybe a cube or the dodecahedron or their counterparts in 4 dimensions. That has sufficiently rich structure in my sense. Or you may be an algebraic geometer, and your X may be a projective variety defined over some field. Your field may be some funny field, like finite field or other. things. But in any case, the object X in this case is the set of polynomial solutions, say inside the projective space, defined by, say, 17 homogeneous polynomials in 5 variables. If you look at the x to the 4 plus y to the 4 plus z to the 4 equals 0 inside P2, then over the complex numbers, you will see a familiar picture of a two-dimensional surface look like that. But your variety may be very high-dimensional or very complicated. That, in my sense, again, has a sufficiently rich structure. Or maybe you like symmetric objects. So your X may be a Coxeter group with a fixed element of given length d. So here the length plays a role of the dimension in previous examples. Your X in this case may be a finite group, like the symmetric group, or maybe an infinite group like that one. A squared equals 1, B squared equals 1, C squared equals 1, A times B to the cube is 1, and so on. And that is the group of symmetries of the first picture you see on the left. Or you may freely modify the exponents that you see on the top of A, B, and B, C, and CA. And you may replace those exponent 3, 3, 3 by something else like 2, 3, 7. And then you get some more exotic groups, like the group of symmetries of the picture that you see in the right. In any case, all these groups with one fixed element, any element, qualifies as an object with sufficiently rich structure. Or, here's my favorite object that I will not define, but which is the topic, secretly a topic of this talk. Your X may be a tropical variety of dimension d. So the adjective tropical is there in honor of the Imre Simon, the Brazilian mathematician, who first started studying objects from tropical point of view, whatever that may be. So I don't want to be very precise here, but later I'm going to show you one nice example of a tropical variety. In any case, this X is a piecewise linear space, as you see in the picture drawn, which is often, but not always, is obtained by tropicalizing algebraic or analytic objects. So for example, if you have a complex algebraic variety embedded inside some projective space, then you can perform this operation called tropicalization and get one of these pictures. And these pictures still remember something about the objects that was tropicalized. But perhaps even more interestingly, even when such structures are not obtained by tropicalizing something else, as an abstract structure itself, it has fascinating properties. So this X, again, qualifies as an object with sufficiently rich structure. So here's our list. And I'm sure that if we try hard enough, we can enlarge the list on and on and on. So apparently, these are all very distinct type of mathematical objects. Sometimes there are certain clever constructions which bridges one territory to some other territory, but this is not always possible. If you're an algebraic geometer, for example, you may well be aware of the fact that when you have a rational polytope, you can construct a projective variety out of it. But you cannot perform such an operation when your polytope is not rational. And in a sense, most polytopes are not rational. And if you're a representation theorist, you may know the fact that when your Coxeter group is coming from a crystallographic root system, then the structure of it has something to do with the geometry of the flag varieties, which is a projective variety. But such construction is not always possible. And in a sense, most Coxeter groups does not arise in this way. So what do you expect such objects to have in common? And the answer is, of course, the Hart-Lefschetz and Hodge-Riemann relations. Hodge-Lefschetz theorem is very classical, but Hodge-Riemann is perhaps less known. And the first person, maybe, to recognize the importance of this second one, the Hodge-Riemann relation, is an Italian mathematician. So here I digged up a letter from Serre to Grothendieck in the 60s, which is perhaps the first mention of the significance of this Hodge-Riemann relations. So Serre says that there's this young Italian, Bombieri, who is working on zeta functions. So they were talking about the Riemann hypothesis. And he mentions this condition. He noticed all by himself that it was necessary to prove that the intersection form on primitive algebraic cycles of half dimension is definite. So that is the Hodge-Riemann relation. And it's all over. So every object that I have introduced so far satisfies or conjecturally satisfies this condition. So I'll be a little bit more precise in the next slide. And apparently this, in each one of these contexts, this definiteness on the primitive space has surprising consequences. So here's the belief. So it's not the mathematics. It's some sort of religion. So given any object X with sufficiently rich structure, you should be able to cook up an associated triple. So in fact, the real picture is slightly more complicated than that, but I'm going to assume for simplicity that your object X happens to be smooth, whatever that means, in some categorical sense. Then in that case, the expectation is that you should be able to associate a triple objects to X. The first one being a graded commutative algebra, say over the real numbers, say A of X. So it's graded from Q equals 0, Q equals 1, all the way up to Q equals D, where D is the dimension of your object X. Of course, the notion of dimension depends on the given context. That's some sort of cohomology ring associated to X. And secondly, you should be able to find a natural map, linear map, going from the top graded piece A to the D, going to the base field real numbers. It's just a linear map that you call the degree map. And thirdly, you should be able to find an open convex cone in the first graded component. So remember, so our A of X is a graded algebra over the real numbers. So if you just look at one graded piece, say A1, it's a real vector space. Let's say finite dimensional. And inside that real vector space, you should be able to find a non-empty open convex cone, K, which is somehow naturally associated to X. Of course, this is not a definition or anything. So the whole point of this business is the finding the correct triple associated to X. And there's no universal definition what would be the right triple associated to X. But in each one of the cases that we have encountered so far, the triple was so naturally associated to X, such a way that you tend to say that you'll know when you see the correct triple. And then one expects the following versions of standard conjectures to be true for any such X. These are the Hodge-Lefschetz and the Hodge-Riemann relations. And it's a certain statement about the triple associated to X. Let's say you pick any element L inside the cone K, the third entry of the triple. And you pick an index Q, which is at most half of the dimension. And firstly, you expect to have the analog of the Hodge-Lefschetz theorem in Kähler geometry. It says that the repeated multiplication by the chosen element L, always coming from the convex cone K, gives an isomorphism between complementary degree pieces of your cohomology ring A. So it goes from AQ to the A to the D minus Q for every Q. So another hidden part of this religion is that you must have the Poincare duality in any case. So A to the Q and A to the D minus Q are expected to have the same dimension, but this statement is a different one. It says that there is a particular type of isomorphism between these two vector spaces of the same dimension. And that isomorphism is attained by repeated multiplication by an element coming from your Kähler cone K. That's the hard Lefschetz. And here's the tricky part, the Hodge-Riemann relations. This was the part that was mentioned in the letter of Serre. It concerns a certain bilinear form defined on the space A to the Q. The bilinear form is defined by saying that you're going to map a pair, H1 and H2, both of the same degree Q, to the up to some sign, minus 1 to the Q, degree of the L times D minus 2Q times H1 times H2. Okay, so what just happened? So the degree was our second component in our associated triple, and it turns an element of top degree to a number. So the end result is a number. So how do you get the top degree element? You take your first entry, H1, and apply the hard Lefschetz isomorphism in the first part so that it lands on a complementary degree. And then you compare it with the second element, H2, which has degree Q, so that you get a top degree element. And you apply this degree map to turn it into a real number so that you have a real valued bilinear form, symmetric. And the statement is that that symmetric bilinear form is positive definite, not on the whole space, but on the kernel of the multiplication by L to the D minus 2Q plus 1. So this D minus 2Q was the exponent that gives you the isomorphism between the complementary degrees. And if you go one step further by multiplying L one more time, it will create a kernel. And the statement is that if you restrict the bilinear form to that kernel, it should be positive definite. In any case, it's a certain statement that some matrix is positive definite. And that kernel was what was referred to as the primitive part in the letter I've showed you before. So that was it. There are two surprising facts. First one is that these two properties are very ubiquitous. No matter what object you are interested in, eventually the belief is that you will end up improving one of these or both of these. And second surprising fact about these properties is that they are quite fundamental and they are actually useful in proving other assertions which may be more appealing to your intuition. So there are most of these cases, these statements which may seem convoluted at first sight, but they are discovered by concrete motivating problems. There are some very concrete numerical inequalities that were observed concerning each one of these objects X. And people try to explain these inequalities and end up in the same type of properties. So let me try to tell you a little bit of the discoveries in each cases. Of course, there is one hard Lefschetz theorem that actually involved Lefschetz. This is the case of Kähler manifolds. And this statement is quite old. It was proved by Lefschetz in the 20s in such a way that was very clear to him, but not to anyone else. So people tried to understand his proof better. And then Hodge developed his theory of harmonic forms and noted that he can use his theory to actually justify his Lefschetz claim. So Hodge proved Lefschetz theorems in 33 using his theory. And in 36, he gave even more correct proof. And in 41, he gave even more correct proof. But still, it wasn't absolutely clear to everybody else. And finally, Hermann Weyl in the 43 gave a proof that was supposed to be understandable to every intelligent human being. So that was the story about compact Kähler manifolds. And there was a similar story about convex polytopes. People tried to prove the statement in various generalities, and they had similar difficulties. Steenbrink proved in the 70s the first statement, and Saito later gave a correct proof. But at that time, very, very few people understood his theory. Later, Beck-Molen came in and proved a purely polytopal argument. And 3 years later, he gave even more correct proof of the same idea. And finally, Carew proved it in full generality. One of the striking application of the Hart-Lefschetz in this case was given by Richard Stanley, who used the Hart-Lefschetz theorem in this context to prove McMullen's G conjecture. This gives a complete numerical characterization of possible sequences f0, f1, dot, 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 f to the d, where fi is the number of I-dimensional faces of a simplicial convex polytope. So if you give me any sequence of non-negative integers, and I see whether it passed the test of the G conjecture. If yes, there is a simplicial polytope having that many number of faces in each dimension. If no, there is no such polytope. Hodge-Riemann relations in this context also has some classical application. Perhaps the best known and most appealing case is the Hodge-Riemann in this case, in the special case for Q equals 1. Hodge-Riemann for Q equals 1 for all polytopes is in fact equivalent to an inequality in convex geometry and analysis known as the Alexander-Ventral inequality for all convex bodies. It's some sort of isoperimetric inequality, and it has fundamental applications. For projective varieties, you can associate some natural triples, in fact, many different triples. And there is one triple that Grothendieck cared much. And for that triple, the statement that Hart-Lefschetz and Hodge-Riemann holds is still open. It's known as the Grothendieck standard conjectures on algebraic cycles. He was led to this statement, and it's also relevant to the letter I showed you before, because it immediately implies the Weil conjectures on the number of points over a finite field, and in particular, the Riemann hypothesis for finite fields. So later, Deligne was able to prove the Weil conjectures without proving Hart-Lefschetz and Hodge-Riemann, and that made Grothendieck somewhat mad. So this statement is still open, but everybody believes it to be true. And for Coxeter groups, this was a very recent result of Elias Williamson, and it is also fundamental in this context. They use it to finally prove the various Cousin-Lustig conjectures on the positivity and some Hecke algebras and so on, and also the conjecture of Sapsiragel. For tropical varieties, or any other object that you like, the statement is yet to be formulated. But what I want to show you today is one very special class of tropical varieties which definitely satisfies the Hart-Lefschetz and the Hodge-Riemann relations. So the object that I'm going to talk about is much more modest than the rather complicated objects that I have shown you before. So in the simplest setting, the object is simply a graph. So nothing can be simpler than a graph. Of course, you can ask hard questions about simple objects, but as it is, this is maybe one of the simplest mathematical structures. It has only just vertices and edges. You tell which are connected to which. So Haslett-Whitney, before he turned to all this stratification and singularity and characteristic class business, was trying to prove the four-color conjecture for planar graphs. And with his teacher, Birkhoff, he tried to make the study of four-color theorem more systematic and introduced the following polynomial, one variable polynomial associated to any graph. This is the chromatic polynomial, and the value of this polynomial at a particular natural number q is the number of ways to color your vertices of the graph using q colors, under one restriction that you need to use two different colors when two vertices are connected by an edge. So this may be one example. So if you want to know in how many different ways you can color that graph using two colors, what you do is you plug in q equals 2 to that polynomial. And you see the value 0. So you know that you cannot color that graph using two colors. So what can you say about the chromatic polynomials in general? So this was the conjecture of Reed and Hogarth. So whenever you write down a chromatic polynomial for any graph, and you read off the sequence of coefficients, then you should always see that quadratic inequality. ai squared is larger than the product of ai minus 1 times ai plus 1. Let me try to convince you that there is something counterintuitive about this statement. The first thing that's counterintuitive is that this statement is a conjecture. It may be true or false, but the fact that this is not obvious to justify is surprising because it is a statement about all graphs. It's not a statement about some subtle class of graphs like planar graphs. And nextly, the conclusion of the conjecture is some very simple numerical inequality that are supposed to be universally true. How can you not succeed to prove this type of statement by a simple inductive argument? This is surprising given the fact that the invariant that we are looking at is actually an inductive invariant. So how do you compute the chromatic polynomials? This is the only, in a sense, only way to compute the chromatic polynomials, the method of deletion and contraction. There is a recursive algorithm to compare the chromatic polynomials of three graphs, one obtained by deleting one edge from the original graph and the other obtained by contracting the other edge of the graph. And this algorithmic description makes the prediction rather interesting. It says that chromatic polynomial is by definition sum of chromatic polynomials of smaller graphs, but taking sum of sequences does not preserve the validity of the conclusion of the conjecture. So there must be something more subtle behind the scene here. So let me skip the second example since I'm a little bit short of time. But there are similar, very elementary type of conjectures that says that you should see some sort of a convexity somewhere from a very elementary combinatorial objects. So where is this convexity coming from? And the answer is that, in fact, there is a hidden Hodge-Lefschetz and the Hodge-Riemann relations behind these elementary combinatorial objects like graphs. The relevant object here is actually the combinatorial structures are called matroids, which from modern point of view form a special class of tropical varieties. So there is this purely combinatorial object called matroids, simultaneously discovered by many, many people, which has some formal definition. It is a structure on a finite set. It's a finite structure satisfying axiom this and that. You don't really have to care about those axioms at this point. But there is a canonical way natural way of constructing such purely combinatorial objects starting from a geometric configuration of points in a projective space. You basically record the linear dependence and independence of the vector configuration in a vector space over a field. And it may happen that, just like the case of polytopes and the Coxeter groups, this purely combinatorial object may or may not be coming from certain algebraic or geometric considerations. For example, the first matroid that you see on the left is the Fano matroid, and that one is coming from a field if and only if your field is characteristic 2. And the other one, the right one, the non-Fano one, is realizable if and only if your field is characteristic not equal to 2. And there are some exotic combinatorial creatures not coming from any field, but over some division ring, and so on and so on. And it is a believed fact that almost all matroids are not coming from field, just like polytopes and Coxeter groups. These combinatorial creatures have lives of their own. And you can generalize the previous conjectures on the convexity or log concavity of certain combinatorial invariants on graphs and matroids to generalize it in this setting. In fact, this invariant of a matroid would imply the previous conjectures, say, for on the chromatic polynomial of graphs. So what could be the possible source of these inequalities? These are expected to be universally true for any such objects. And in fact, the recent development in tropical geometry suggested a new point of view on these purely combinatorial objects. It tells you that what we used to call matroids are a very special class of tropical varieties, a certain piecewise linear geometric object that is sometimes obtained by tropicalizing algebraic varieties. And these matroids are, in fact, exactly the class of linear tropical varieties in a precise sense. And the point is that any tropical variety can be associated to a natural triple. It has a cohomology ring, it has the degree map, and it has the ample cone. In fact, we can associate such triple to any matroid or any graph. And for the case of matroids, we can be very explicit. So there is, I guess, no point in reading this definition at the moment, but I want to convince you that there is a very concrete way of describing these cohomology rings associated to any tropical variety. And in the case of matroids, it is just this. The commutative algebraists will recognize the first ideal as the Stanley-Reason ideal of some order complex. But the second part, which only involves the linear relations, is what's most interesting. That's not the linear system of parameters, but a very special choice of linear forms that are governed by the geometry of tropical varieties in question. And that's what makes the miracle of Lefschetz and Hodge-Riemann happen in this case. So, in sum, you can associate a ring to a matroid, say for graphs. It is a commutative ring, finite dimensional over the real numbers. And this definition is set up in such a way that this cohomology ring associated to a matroid is a ring of algebraic cycles modulo numerical equivalence on some smooth projective varieties over K when your matroid is realizable over K. So if you believe in Grothendieck's standard conjectures, you expect that this ring to satisfy Hart-Lefschetz and the Hodge-Riemann relations, at least in the case when your matroid is coming from a field. And here's the second ingredient to make sense of the Hart-Lefschetz and the Hodge-Riemann relations. Again, there is some very explicit and combinatorial way of describing the degree map. This is a combinatorial analog of the fundamental form or orientation. So there is a linear map going from the top graded piece of our combinatorial ring going to the real numbers, which is determined by some combinatorial property. You can construct it. And lastly, you can give an explicit description of the open convex cone that I referred to as a Keller cone in previous examples. So there is some very nice combinatorially described universal convex cone living inside A1 to the m in each m. And you can see what will happen next. So no matter whether your combinatorial object is coming from a field or not coming from a field, you will always have the following properties. If you pick an element L from the convex cone that I told you before, then the following should happen. The repeated multiplication by that degree 1 element should give you an explicit isomorphism between the complementary degree pieces of what you would call cohomology ring in this context, one for each matrix. Secondly, you would have the Hodge-Riemann relations. If you define that symmetric bilinear form on the q-graded piece of the cohomology ring, as we did before, then that symmetric bilinear form is positive definite on the primitive space. That is, the kernel of the multiplication by L to the 1 more than that would give an isomorphism to the complementary degree. So in the end, the first statement boils down to showing that some matrix has non-zero determinant. Second statement boils down to the statement that some matrix has positive determinant. And why is the Hodge-Riemann relations has anything to do with the convexity phenomenon that we have seen before? So this is essentially the same thing why you would have the Alexander-Ventral inequality we would expect for mixed volumes of convex bodies. If you apply the Hodge-Riemann relations in the special case when your Q equals 1, the simplest non-trivial case, then it would say that some matrix has exactly one positive eigenvalue in the end. And you can use that to evaluate the determinants of many, many 2 by 2 minors. And it tells you that these minors have exactly one positive and one negative eigenvalue. And the concavity phenomenon that you have seen, say B squared is larger than A times C, is same as saying that this symmetric matrix, A, B, B, C, has non-positive determinant. And that is a very special case of the Hodge-Riemann relations. So let me end with a brief indication of how you would prove something like this in general. Of course, proving Hart-Lefschetz and Hodge-Riemann relations for complicated objects is a difficult task, as was observed by the history on the subject. But if you start from a very explicit and combinatorial, simple objects like graphs, then there are apparently universally effective method for accomplishing this sort of job. And that is what we did to prove these statements. In this case, what we do is the following. For any two objects of interest, which I view as a tropical variety, a certain geometric object, we show the following. We show that so long as these two objects have the same dimension, there is an explicit way to deform one thing to the other thing. This operation is a finite operation that we call flip. And it is very much analogous to the flip that you see in the piecewise linear topology. It changes the structure of your combinatorial object locally. It doesn't have a real global effect. At one time, you change only a small part of your object. But the miraculous thing is that oftentimes, in this case, you can flip connect any object to any other object that is of interest. In PL topology, this is known as Pachner theorem. And in birational geometry, people call this weak factorization theorem for birational maps. And what you try to show, after proving that any object can be flip connected to any other object, is that the validity of the Hart-Lefschetz and the Hodge-Riemann relations is preserved under one flip. But this analysis is much easier than the analysis of the global object when you're trying to prove the whole thing at a single stroke. And this is, in fact, how they proved it in the case of polytopes and also, in a certain sense, to the Cox-2 groups. But what's maybe interesting in this new case of tropical varieties that were not observed before in the case of polytopes, for example, is that when you try to do this connection between two objects of interest, the intermediate objects that you have to pass through do not belong to the class of objects that you were originally interested in. So intermediate objects in this case are the tropical varieties with perfectly nice cohomology rings and ample cones and so on. They all satisfy Hart-Lefschetz and Hodge-Riemann relations. But they are not coming from matroids. They are just tropical varieties. So sometimes it is very helpful to enlarge your world to connect any two things inside the class of objects that you are interested in. So this proof, I think, gives one justification of looking at objects in a tropical way. Why study tropical varieties? It's one justification. And it also indicates, I think, a good hope that there is a nice class of tropical varieties that you want to consider. And for all of them, in fact, the Hart-Lefschetz theorem and the Hodge-Riemann relations are valid. And I hope this model can be used in some other cases also with similar structural properties, so to establish the Hart-Lefschetz theorem and the Hodge-Riemann relations. Thank you. I'll stop here.